So again, we could use a table of values, but the strategy that we're going to be using first, if you remember how to do it, is to factor things, find all of our x-intercepts, find all of our y-intercepts, and then just use the fact that we know that an x-cubed graph, its end behavior is going to be like a positive line because the leading coefficient is a positive 1. So factoring this one, this is an easy one to factor because first of all, we notice that there's a common factor of x. And because there's a common factor of x, we don't have to use long division, synthetic division, any of the factor or remainder theorems for this one. Because as soon as we take that x out, the biggest thing to factor is a quadratic, and you know how to factor quadratics. Now, if you wanted to find the x-intercepts, you'd plug in 0 for y. So as far as showing your work, now I'm plugging in 0 for y. And then I can split this up and say that x equals 0, x equals -3, and x equals 2 are my 3 x-intercepts. Okay, the fact that x equals 0 is one of my x-intercepts also tells me that y equals 0 is my only y-intercept. But if you wanted to, you could still plug in 0 for x and see that you have the point 0, 0 for your y-intercept as well. Now, when you go to graph this, what you'll do for graphing it is you'll plug in all of your x-intercepts. So there's 0, -3, and 2. And label those points. And then finally, you know that it acts like a line, so it's got to come here. We don't know how high it's going to go or how low it's going to go. Just make it swoop through, make sure it goes through the points as best as you can. And we're not concerned about how high it goes for this maximum or how low it goes for that minimum. We just want to get a sketch of this graph. So this one was really straightforward and easy because the factoring was easy. The reason I want to do the other one in the example is it is quite different than the one that you have there. So if you should have space, you should have space on the next page in the column here to do this one. Now, in order to factor this one to find all the x-intercepts and all the y-intercepts, you're going to have to use your factor theorem and remainder theorem, so it's good practice. First of all, if you plug in 0 for x, you can see right away that 0 plus 0 plus 0 plus 0 minus 6 will give us a y-intercept of -6. Now, if we can factor this one, what are the possible answers that could be factors? Remember how we find that out? 1, 2, 3, and 6. In order to factor this, the last number is a -6. So if we were able to factor it, it would be 1, 2, 3, or 6. And it could be positive or negative for any one of those. So what we need to do is try and find one that would work. Now, mental math-wise, start with the 1s, because that's going to be easier to figure out mental math-wise as opposed to the bigger numbers like 6. So if we plug in 1, we're going to get 2 minus 1 minus 14 gets us to -13. Plus 19 gets us to 6. Minus 6 gets us to 0. So when you plug in 1, you get 0. What does that mean for our factors? What is a factor? X minus 1 is a factor. So because x minus 1 is a factor, we can set up our synthetic division, 2, -1, 14, 19, -6. One thing I always do when I'm setting up my synthetic division is after I write it down, I make sure that I haven't missed putting in a 0. Because sometimes there's terms missing, like if there was no x squared or there was no x, you have to remember to put a 0. So make sure you check that afterwards. This wasn't the case in this one. What number do I put outside? 2, -1. -14, yes, there it is. Thank you. That would have caused us problems. And we would have noticed, because if I had that positive 14 there, I should get a remainder of 0. And if I made a mistake and I don't get that remainder of 0, either I wrote down something wrong, or I did some math wrong, or my initial factor was actually wrong. So you'll have to go back and check some things. What number goes outside? A 1. Good. So now, we bring down the 2. 2 times 1 is 2. Add 1. 1 times 1 is 1. Add -13. 1 times -13, -13. Add 6. 1 times 6, 6. And sure enough, we get our remainder of 0. So we can write our first division statement. Okay, our first division statement, the result of this tells us, and I'm going to write f of x for my polynomial. We divided by x minus 1, and we got 2x cubed plus x squared minus 13x plus 6 as our second factor. And our second factor is still an x cubed, and so we have to go through this process again to see if we can find another factor. Again, we're going to look at this 6, and we get 1, 2, 3, or 6, plus or minus, plus or minus, plus or minus, plus or minus. And we need to try and find one that makes that second one equal to 0. So chances are we'll start with 1. 2 plus 1 is 3, minus 13 is -10, plus 6 does not equal 0. Let's call this, I'm just going to call this one temporarily g of x, because we've used the function f of x to describe the first one. So I found out that when I plugged in 1, I did not get 0. When I plug in -1, I'm going to get -2 plus 1 gives me -1. Plus 13 gives me 12. Plus 6 does not work either. So next I'd probably go to 2. 2 cubed is 8 times 2 is 16 plus 4 is 20. Minus 26 is -6 plus 6 is 0. So when I plugged in 2, I got 0. What does that mean? X minus 2 is a factor. And so now we can do synthetic division with that second function. The coefficients are 2, 1, -13, and 6. And we would put a 2 outside. Now we should get a remainder of 0. Bring down the 2. 2 times 2 is 4. 1 plus 4 is 5. 2 times 5 is 10. -3. 2 times -3, -6. Yes, it worked. So now we can write our original function f of x. We found out that x minus 1 was a factor from the first one. And now we found out that x minus 2 is a factor from the second time, and we're left with 2x squared plus 5x minus 3. Finally got to a quadratic, which you know how to factor. If it can be factored, sometimes the last one can't be factored, and then you would be done. And sometimes you could only solve it with the quadratic formula, so then you'd have to use the quadratic formula to find the last one. But in this case, it'd be 2x and x. In order to get a plus 5 and a -3, we'd have to have plus 3 there and minus 1 there. So if we want to find our x-intercepts, oops, we plug in 0. And then split it up, so x equals 1, x equals 2, x equals positive 1/2, and x equals negative 3 are our x-intercepts. So once you've found all of your x-intercepts and your y-intercept in this case, which we did right at the beginning, and we know how the end behavior of this one works, we can do a quite accurate sketch of this graph. We're going to have 1, 2, 3, negative 3 as 1. We're going to have 1, 2, and negative 1/2. I'll label those points. And we have our y-intercept was positive 6, so I'll label that point as well, 0,6. It is not enough just to put ticky marks along the bottom or up and down. Was it negative 6? Yes, thank you. Thank you, thank you. There it is down there. It's not enough just to put ticky marks and assume that each one is 1, because you can make a graph where your scale is going by 2s, you can make a graph where your scale is going by 10s. So on your final exam, they require you to label points to give an indication on your graph for what the scale is. So if I hadn't labeled 0, negative 6, and I just went 1, 2, 3, 4, 5, 6, and drew it there, you would lose a 1/2 a mark. Okay? If you put a 1 here, or a negative 1 actually, because that's actually going down 1, that would indicate that your ticky marks are all going by 1. Then if this point wasn't labeled, it can be deduced from the fact that you labeled something. Okay? But you have to label something to give an idea of what your x's are, and something to give an idea what your y's are, if you're going to label points on both your x's and your y's. You notice our last example, we didn't have to do anything on our y's because we didn't know anything about our y values, because we just had x-intercepts and our y-intercept was at 0. But this one, we know something about our y-intercept being at negative 6, and we know our x-intercepts. So now we've got 1, 2, 3, 4, 5 points labeled here. Our original graph was an x to the 4 graph that was positive, so we know that it acts like a parabola that goes like this. So from our end behavior, we know it has to start coming down here. It's got to go through this point next. Woo! This one, this one, this one. All right, I have something in this graph that I'm not happy with. I don't like how I swooped out too far and then had to come back in time. So this part here is a little bit problematic, because the way that it goes too far out, it technically isn't a function. So that would be something that, depending on the severity of your swoopiness, might be a deduction on the final exam. So I'm going to take my time and be a little bit more careful here second time through. Put arrowheads on the end of my graph. Okay? It might not be that that is the minimum. We don't know that. Okay? So now I tried to do a little bit better job of not swooping out too far. This graph would get full marks. I'm going to draw another graph over top of this in purple. Okay? Again, it goes down deeper. Now this one for sure doesn't even have this y-intercept as a minimum. We're a little bit presumptuous in assuming it's a minimum, but you want to do that because when you have points, and from your connect the dot experiences in grade 1 and 2, you like going straight to the dot and then going from there. This purple graph probably is more accurate than the black one because it was easier for me to draw, to go down further and then swoop up through the points like that. That's probably a more accurate graph, but we don't know how far it goes down and where that minimum is. You can find it on your graphing calculator right now, and you're going to be able to find it next year with calculus. So either one of those would be fine. The questions you can do now are 7 and 13.